In this video, we are going to look at the rate and extent of reaction chapter in grade 12 from term 2. First, let's quickly go through the chapter objectives. These are the things that you need to know after completing the chapter. So number 1, you have to differentiate between endothermic and exothermic reactions. Number 2, you have to know the meaning of the word rate of reaction. You have to know how to calculate the rate of the reaction in terms of reactants getting used up and products that are forming. After completing, you have to know how to measure rate of reaction experimentally. You have to know the conditions for effective collisions according to what we call the collision theory. I'm sure you already done this in grade 11, but we'll look at it again in this video. You have to know how to use the collision theory to explain how certain factors that we're going to talk about affect this reaction rate. After completing, you're expected to know how we can change reaction rate or improve it. And you have to know how to interpret and understand the Maxwell-Boltzmann distribution curves. This is one of the last topics that we'll talk about in this chapter. In your test or exams, you'll be given a scenario whereby you're given a factor that is being investigated that will affect rate of reaction, and you have to know how to calculate those questions that are related to that factor. And perhaps most importantly, you have to know how to use stoichiometry that you learned in grade 11 to solve these problems. They are going to involve a lot of stoichiometry. So make sure you are comfortable with that. If not, I'll make videos. So make sure you subscribe, you stay close to this channel, and then you'll learn a lot. Let's look at the introduction. Let's say a match is burning, a car is slowly rusting, tomatoes are rotting. What you already know is that all these three things represent chemical change. And if we really zoom in into them, we can see chemical reaction taking place. Then what you should know is that this reaction proceeds at different speeds, or what we call at different rates. This means the time at which the match is burning away will not be exactly the same as the time it takes for rust to completely destroy a car. What you'll probably come up with is that the match will win the race and the car would come last, because rusting could take years. As we know, some of our parents have those older cars at home and they're just sitting at the backyard. If you go and check that car, you'll see that it takes a really long time for it to be destroyed by rust. And then you can agree that the tomatoes would maybe take a few days without putting them in the fridge to completely rot away. Then in this chapter, we're going to look at why reaction proceed at different rates and how we can change that rate of reaction, because sometimes these rates are not favorable. Imagine you're working in a farm and you're trying to produce a fertilizer, for example. You cannot wait for 3 days. If that fertilizer takes 3 days to be completely done, you have to find a way to speed up that reaction. So this is what the chapter is basically about. Let's dive into it. First, we'll look at the revision from grade 11. These are some of the things that you'll need to know for you to be able to master rate of reaction in grade 12. You have to understand that there's energy change when bonds are being broken and the new bonds are forming in a chemical reaction. I'm not going to go deep into explaining this concept because you've already seen it from grade 11. When these bonds are broken, energy is absorbed from the environment, and we call those reactions endothermic. We'll see why as we go on. When bonds are formed, energy is then released into the environment, and these are what we call exothermic reactions. So now if we add the energy when the bonds are being broken and the energy when the bonds are being formed, we get the net energy change. And this net energy change will tell us whether a reaction is endothermic or exothermic. So now let's talk about what we call the activation energy. As you'll recall, in order to start a reaction, energy first needs to be absorbed to break the bonds. So you have your reactants, you have to break all those bonds so that you can now start a reaction. So the activation energy is that minimum amount of energy that you need to kickstart a chemical reaction. Now let's talk about enthalpy and enthalpy change. Enthalpy, which we denote by capital letter H, is the total amount of stored chemical energy. What do we mean by stored chemical energy? We mean the potential energy of the chemicals. Think of it as an object that is placed at a certain height. If you let go of that object at a certain height, it is now going to drop. So it's going to release its potential energy in a form of another energy. So our chemicals also behave that way. They have potential energy which they want to release into some other forms of energy. So this stored energy, we call it the enthalpy, or capital letter H. Now the change in enthalpy, which we denote by delta H, represents the heat of the reaction. This is measured in, well, some books say kilojoules per mole. Some books will tell you that it's only kilojoules, but don't worry a lot about that. We'll see where it's kilojoules and where it's going to be kilojoules per mole. Now the change in enthalpy is basically the net energy change that we talked about earlier on. Now let's look at the endothermic and exothermic reactions. We will compare all these things one by one. Endothermic reactions have more energy that is absorbed than it is released. Exothermic have more energy that is released than is absorbed. Most of the time we'll only say endothermic absorb energy and exothermic release energy. But in all honesty, there are more energy that is absorbed in endothermic than it is released, because energy is going to be released but a little amount compared to what is already absorbed. Okay, vice versa when we go to exothermic. Now the energy of the reactants in exothermic is less than the energy of the products. The energy of reactants in exothermic is greater than the energy of the products. We'll see a sketch very soon. The change in enthalpy for endothermic reaction is positive, or it increases, while in exothermic reaction, the change in enthalpy, or delta H, is going to be a negative value. Let's draw a graph of potential energy, EP in kilojoules, versus the course of the reaction. So as the reaction proceeds. Now we'll show the energy of the reactants and we'll show the energy of the products under endothermic reactions. So remember we said the difference in these energies is called our change in H, or the change in enthalpy, or the heat of the reaction. So here you can check that change in enthalpy is given by the energy of the product minus the energy of the reactants, and in this case it's positive. So let's look at how our diagram is going to look like. Here's the energy of the reactants. It goes up and then drops to the energy of the products. Why does it do this? Okay, first let's define the activated complex. This is the maximum point on your graph, on your potential energy graph. And from the energy of the reactants to the activated complex, we have the activation energy. Remember, activation energy is the energy that you need to start a chemical reaction. So our reactants have this little energy. We have to put in some more energy up to a point where we call activated complex, where now things become critical and then a reaction takes place. After the reaction takes place, it's going to now release some of those energy until we get to the energy of the products. So you already seen this in grade 11. Now what does a catalyst do to this graph? It's going to now decrease the amount of activation energy that is needed for this reaction to happen. So basically a catalyst will save you energy, which is now money. So remember, you own a firm and you need that energy to now make the fertilizers. You need to input energy. It might be in the form of heat or electricity that you buy. And when you have a catalyst, now you're going to need a small amount of energy. So you're going to save a lot of money using a catalyst. So basically a catalyst is something that is added in your chemical reaction. It doesn't take any part in the reaction, but it does speed up the reaction. Let's do the same for the exothermic reactions. So we have the potential energy versus the course of reaction graph. In this case, our reactants have a little bit higher energy than the products. And your heat of reaction now, energy of the products minus energy of the reactants, the products are, let's say, 5 kilojoules. The reactants are, let's say, 10 kilojoules. So if you take 5 and you minus 10 from that, you get a negative value. That is why the heat of reaction for exothermic is negative. Let's see how the graph looks like. So we have the energy of the reactants. We still need energy input before we go to the critical point, and then we go to the products. That critical point is the highest point, which we call the activated complex. The energy inputs from the reactants to the activated complex, we call it activation energy. Now, if we put a catalyst in there, the activation energy is going to be lowered. Okay, this is going to be very important in our chapter as we go on. Okay, we are done with our revision. Let's go to the grade 12 stuff now. Make sure you like at this point, guys. Don't go to the next part, to the next second of the video before you like the video and you subscribe to the channel. The rate of reaction. Now, what is rate of reaction? Rate of reaction describes how quickly reactants are being used up or how quickly products are forming during a chemical reaction. So let's express that in terms of math. So rate or average rate is equal to the change in the amount of product divided by the change in time. When we say rate, we mean divided by time, right? So average rate will be the amount of products, basically product final minus product initial divided by change in time. Same applies as we talk about reactants. What is this amount that I'm talking about? This can be in terms of change in mass per unit time, which our units will be something like grams per second. Don't worry a lot about units, we'll see as we go on. Or we can measure rate in terms of change in volume per unit time, which will be in cubic centimeters per second. We can also use the change in the number of moles per unit time, which maybe will be in moles per second. Now let's consider this glass of water and a pill that is about to be dissolved in there, and then we'll draw a graph of the amount of pill that we still have in terms of time. So let's look at what happens. We drop the pill into the water. What is the amount of pill that we still have as time progresses? So we'll plot this graph in real time. So as you can see, we start with a certain amount of pill, but at some point where I'm pointing there, we don't have any pill left. So we say the reaction stops because the pill is fully dissolved. Now if you check the graph, it's not linear. This is because when the pill is still a full pill, there's gonna be a lot of reaction compared to when it's now getting used up. When it's now getting smaller, the reaction will start to be slower and slower and slower until it stops. So the reaction starts quickly, it gets slower with time until it stops. From the point where the reaction starts to the point where the reaction ends, the point where the graph now starts to flatten out. If we take the average gradient there, we get the average rate of reaction. Okay, we'll see this a lot as we go on. Okay, I think it's about time we look at an example. This example says zinc reacts with sulfuric acid according to the reaction below. The mass of zinc is recorded during the experiment and is shown on the graph below. The reaction stops after 2 minutes. Calculate the reaction rate and the initial concentration of the sulfuric acid if 50 cubic centimeters of the acid was used. The graph of rate of reaction of zinc. So on the y side, we have the mass of zinc in grams versus the time in minutes. So we can see initially we have 5 grams of zinc, and it looks like our graph is going to flat out when we now have 2 grams of zinc. What is the time when the graph starts to flat out? That is 2 minutes. The question also tells us that the graph is going to flat out, or the reaction is going to stop at 2 minutes. Okay, first what we can do obviously is to check if the reaction is balanced. Most of the time, they will give you a reaction that is balanced. But yeah, first verify. Now, how do we find the rate of reaction? Remember, this is now the change in the amount of reactant, which is what is the final amount of zinc minus the initial amount of zinc divided by time final minus time initial. So that is where I'm indicating there. So now I can even use mathematics to find the average gradient. This is simple stuff now. So I can say 5 minus 2 as the change in y over 0 minus 2 as the change in x. Remember, 5 goes with 0, 2 goes with 2. So I could have also said 2 minus 5 over 2 minus 0. So this will give me negative 1,5 grams per minute. Remember your units, guys. We have grams on the y and minutes on the x. So this is grams per minute. And someone might ask, what is the negative mean? The negative means things are getting used up because zinc is a reactant. So we expect it to be used up. If we're doing this in terms of hydrogen gas, we'd expect a positive answer to show that the hydrogen gas is being produced, and now the graph will look different from that one. But we'll see that as we go on. Now the question that I come up with is, what is the limiting reagent? So you can see now that we go to stoichiometry from grade 11. So you're going to now revise all those things. I'll make videos on those as well. So make sure you subscribe at this point in the video. Make sure you like the video and you subscribe. Share it with your friends if you want them to get distinctions as well, because I guarantee you'll get a distinction after these videos. Okay, now the limiting reagent, if you remember, is a reactant that is completely used up in a chemical reaction. So if you check the graph of zinc, we start with 5, we end with 2. The reaction stops when the mass of zinc is 2. So this means zinc is not completely used up. In fact, zinc is in excess. So the limiting reagent will be the other reactant that is being reacted with zinc, which in this case is sulfuric acid. Now the second part of the question says calculate the initial concentration of the sulfuric acid if 50 cubic centimeter was used. So for this, we basically need the mass of zinc that is reacted. We then convert that into moles, and then we can find the moles of sulfuric acid that reacted. So that will give us the initial moles. Then we can convert that into concentration using the volume as well. So let's do that. The mass of zinc that is used up is going to be the mass that reacted is the initial mass that we started with minus the mass that is in excess. So this is going to be 5 minus 2, which is equal to 3 grams. So now we know that 3 grams of zinc actually reacted in the reaction. So we need to calculate the number of moles of that zinc that reacted. This is equal to the mass over the molar mass. The mass of zinc is 3. The molar mass of that zinc there is 65 from the periodic table. And we get a value of 0,046 ... mole. The meaning of ... is that I'm not really cutting the decimals, guys. I'm writing everything, but just to conserve space, I'm gonna use the dots to show that there are more things after the comma. So remember, you do not round off intermediate steps. You have to keep all those decimals with you in your calculator, or maybe write them down somewhere. When you substitute in the next part of your question, you can then use the full value. Okay, now we know that 0,046 moles of zinc completely react with the sulfuric acid. So that's a mistake there. It's supposed to be 0,046. So we can use the ratio learned in grade 11. Zinc is to sulfuric acid. What are the stoichiometric coefficients? 1:1. This is what we get after we balance the chemical reaction. So in front of zinc there's 1, in front of H2SO4 there's 1, and then now we know the amount of zinc is 0.046. Now we want to find the number of moles of H2SO4. What we do is we cross multiply. So 1 multiplies N, and then this is equal to 1 multiply 0.046. Then we see that the number of moles of sulfuric acid that reacted is 0.046 mole. This is again the number of moles of sulfuric acid that we started with in the reaction. So the concentration is equal to number of moles over volume. We already have the volume, we just have to convert that into decimeter cubed by dividing by 1,000. So now we get 0.046 as the number of moles divided by 0.05 as our volume. And if you didn't round anything, you get an answer of 0.92 mole per decimeter cubed. That is the unit we're looking for concentration. Okay, good. Let's proceed. Now we'll talk about what are the ways we can use to measure rates of reaction. So there's a couple of ways, obviously, for measuring rate of reaction. In this case, we're going to only look at a method whereby we collect a gas that is being produced using a gas syringe arrangement as shown in the diagram, and we're going to record the volume of that gas at set time intervals. So we also have a stopwatch or a clock to measure the gas and the time at the same time. So the green plunger in the syringe will be pushed out as now gas is produced, because that little straw is dropped inside a reaction flask which is going to produce a gas, and then we put a stopper there so that the gas doesn't escape anywhere else other than going inside the straw. So the plunger is forced out when the gas is produced. Let's look at the reaction that we looked at initially, where zinc metal, so that thing you see there that looks like a rock, it's actually zinc metal that is reacting with sulfuric acid, which is now in blue there. This produces zinc sulfate plus the hydrogen gas. So if now I ask you, what actually are we going to collect in this experiment? You say the hydrogen gas, isn't it? Because that's the only gas that is produced in the reaction, and that's the only thing that's going to fly out into the air, and we're going to catch it into the syringe. Okay, simple as that. So I'll show you what the reactants look like. I'll show you what the products will look like. So zinc will be black, that rock is black. Sulfuric acid will be blue. Zinc sulfate, when we now have zinc sulfate, you'll see a yellow color. When we now have hydrogen gas, you'll see a gray color to show that this is hydrogen gas. Beside that, we'll draw a volume. This is time graph for the hydrogen gas that we collect with the units of cubic centimeters. So basically, we're going to draw the rate of reaction graph in real time. So let's look at the reaction. So now you're going to try to borrow at least 6 eyes, because what you're going to look at is now a metal that is disappearing because it's reacting, time that is now going to run, a plunger that is going to be pushed out because gas is entering, a graph that is going to be now drawn in real time, and the sulfuric acid changing into zinc sulfate. So obviously you're not going to have 6 eyes. You're going to just rewind to the start of the reaction, go back, rewind again. So let's look at the reaction. You can see the bubbles are forming and the gas is released. It's going into the plunger, and then we draw our graph. There's a red dot there which shows that the reaction is now stopped. From there you can see the graph is flattening to show that the reaction is stopped. You can see the liquid now turns yellow to show that zinc sulfate is produced. Okay guys, I'm sure you appreciate these things. Let's look at it again. Okay, good. So now on your graph, you're gonna wanna record the final volume and the final time when the reaction stops. This is going to help you to find the rate of the reaction. So now you can see we are collecting a product, which means we're going to start our graph at a volume of 0. It's going to increase very fast. So if you check the gradient there, it's very steep, and then starting to now flatten out until it's 0 at the red dot. So obviously there's a couple of other ways we can measure rate of reaction experimentally. We can use the change in mass, whereby you have a cotton that prevents water from getting out of your flask, but gas can escape, and then you put that on a mass balance, whereby you record the decrease in mass and you plot that. It's going to give you the rate of the reaction. And you can use the change in color, which are already illustrated here. So the color changed from blue to yellow, which means a product is formed. So you can check the time there and determine the rate. We're going to also use precipitation. Some reaction produces a precipitate. So you're going to put maybe a cross under the beaker. You're going to look over the top, and when now a precipitate is starting to form until it stops, you're going to record your data on a graph and calculate the rate of reaction. Another way you can measure rate of reaction is by using a change in pH. Basically, when you have acid-base reactions, you can check how pH changes. When pH is now stable, that's the end of the reaction. You can graph that and check the rate of reaction. So the rate of reaction can come in many different units, in many different ways, but all in all, we measure how fast the reaction takes place. Okay, let's go to the collision theory. This is very important to understand. First, we're going to define it. What is the collision theory? Collision theory tells us that reactants particles must collide with sufficient energy and correct orientation to form products. Then the conditions for successful or effective collisions are, we only have two conditions. So condition number 1, particles must collide with the correct orientation. What do we mean by correct orientation? I'll show an animation that will quickly explain to you. So that's what's special about my channel. I show you animations to try to make you understand this stuff. But what you have to know again as a chemistry student is that some catalysts function by improving molecular orientation. So it's just going to grab a molecule and rotate it in a way that it's going to have a correct orientation. So that's how catalysts also function. Let's look at a reaction whereby we have potassium chloride reacting with HF hydrofluoric acid to produce potassium fluoride KF plus HCl, which is hydrochloric acid. So now our potassium will be the green circle, our chlorine will be the yellow circle, so that gives us potassium chloride. Our H will be the small red circle, our F will be the big purple circle. Now this is a case where the orientation is not correct to form the products. Let's see what happens. So you can see the reactants just literally bounce off each other. Nothing happens, no reaction takes place. So we don't want that. Let's look at a case where now the orientation is correct. So we still have the same reactants. In this case, we have now HCl and KF. So the products are formed because we had the correct orientation. Rewind the video to see the animations again. Condition 2 for effective collision. Particles must collide with sufficient kinetic energy. So in other words, kinetic energy should be greater or at least equal to the activation energy. Why do we want the kinetic energy to be greater than the activation energy? So that the bonds can be able to break if our molecule doesn't explode into another reactant, then a reaction will not take place. Let's look at an animation again to explain this. You can see we still have the same reactants that are going very slow. Now the orientation is correct, but still the reaction doesn't take place. Why? Because the reactants do not have sufficient kinetic energy. They are not moving fast enough. So no reaction takes place there. Let's look at a case where the reactants are moving very fast with correct orientation. So you can see now a reaction takes place. We now have HCl and KF on our products. So a reaction happened due to the fact that the kinetic energy was greater than the activation energy. Okay, again, rewind the video to watch the animations again for you to understand the collision theory. Now we're going to talk about factors that affect rate of reaction. Here we're going to discuss 6 factors. The first one is temperature. Now, if we increase temperature of a chemical reaction, the rate of reaction will increase. Okay. Now, this topic is very important. You're going to get this for 4 marks in your question paper. One of these factors out of the 6, one of them will be in your exam, in your tests. So this increase in temperature increases the kinetic energy of the particles. So now particles, because they're getting that heat, they're going to now move very fast. So they're going to move very fast. This now makes more particles to have more kinetic energy to overcome the activation energy. So we say more particles have more kinetic energy to overcome activation energy. Or you can just say more particles have more EK greater than EA. When this happens, more effective collision can then take place per unit time. So let's look at an example. We'll draw a rate of reaction graph for products versus time. When we have a small flame, our reactant is now that metal and that liquid. It's arbitrary at this point. It could be any acid and any metal or anything at all. So a small flame will now have a rate of reaction that looks like this. It's going to end there at the blue dot. But now if we increase the temperature or we increase the flame, if you want to visualize it, the rate of reaction is going to be very quick. You can see now the metal disappears very quick. And then you can see the recorded time or final time is sooner than when the flame was smaller. So increasing the temperature increases the rate of reaction, thereby making your waiting time very small. But as you can see, the final volume, or because now I'm talking about cubic centimeter, the final volume of gas produced is the same. This is very important. Final volume is the same. Doesn't matter when the flame is bigger or smaller. If the reaction go to completion, the final product is the same. In this chapter, we're interested as to what is the time it takes to produce those products. Okay, so the time is going to be different, but the products is going to be the same. Now let's look at the concentration. Usually in concentration, we'll be more concerned with gases, but also with aqueous solutions and other things. So increasing concentration will increase the rate of reaction because more particles will be present per unit volume. Means adding more of the reactants. So more particles are going to be present. Then more of those particles, now a greater ratio, will have more kinetic energy to overcome the activation energy. And now more effective collision can be witnessed per unit time. But then again, what are the benefits of having me as a tutor is that I show you the visuals, okay? You can be able to understand these things visually. So now I draw again the graph of products versus time, the same kind of scenario. Now this is the normal graph with no changes in the concentrations. You can see the reaction is going to stop there at the blue dot. We record the time and the volume or the amount of products produced. Now we increase the concentration of what we'll assume to be the excess reagent. So let's say the liquid is the excess reactant. If we increase the excess reactant, what will happen? The reaction is going to be much quicker. The disappearance of that metal is going to be much quicker, but we still produce the same amount of products because the limiting reagent is still determining the amount of products. But what if we actually increase the limiting reagent, or we increase the amount or the concentration of the limiting reagent? What happens? The reaction is going to be quick as well, but the amount of product is going to be more because we're increasing something that made the reaction to produce less products. If we increase that, the reaction is going to produce more products. So by increasing the limiting reagent, we are making more products. Okay. Let's go and investigate another factor called a catalyst. So the presence of a catalyst, guys, will decrease the activation energy. Now, when we decrease activation energy, more particles are going to have more kinetic energy that is needed to overcome the activation energy because the activation energy is lowered, right? So more effective collisions can be expected per unit time. And if we look at an example, here are normal conditions with no catalyst, completion, that time. Now we now add a catalyst. By adding this catalyst, the reaction is going to proceed much quicker, but realize that the products are still the same. Now let's focus on the surface area or the state of division as our fourth factor that affects rate of reaction. So if we increase the state of division, in other words, we use powder instead of chunks. So let's say you have sugar to sweeten your tea. If you use a big chunk of sugar, you're gonna stir a lot or a long time before it's fully dissolved than if you use a very fine powder of sugar. Then it's gonna take a small amount of time to quickly dissolve in the tea. So increased state of division is going to increase the rate of reaction. We'll understand this with visuals as well. So if more surface area is exposed to collisions, this will increase the number of particles that will undergo collision. So if we have a block, we can calculate the surface area all around that block. If we now break the block into 2 halves, or 4 halves, or 6 halves, we can now increase the surface area or the amount of faces. So the more the faces, the more the collisions, and the more the effective collisions per unit time. So let's look at a visual representation of that. This is normal surface area, a big chunk. The reaction is going to proceed. It's going to end there at that time. But now, if we break this in half, look at what happens to the reaction rate. It's going to be much quicker because the surface area is increased. So now we need less time to actually finish up the reaction. But remember, as you can see, the products are still the same amount. It's still the same chunk. It's just broken into pieces. Okay, someone with a great mind can ask, but how does that increase the rate of reaction? Think of it this way. A big chunk and a divided chunk. In a big chunk, the liquid can only penetrate the outer side of that chunk. So it's going to eat away the outer side until the inside, and then the chunk is disappeared. But now when you divide that chunk into many smaller pieces, if you take that chunk and you divide it into powder, now the reaction can still eat away the side of the chunk, but in this case, it's going to also penetrate the other faces where you actually cut the chunk. So it's now going to be much quicker, but the product's still the same. Let's investigate the nature of reactants. Here we're just going to talk about the fact that the physical and chemical properties of other molecules will make them more reactive than others, right? This only makes sense. The speed of someone else will not be the same speed as the speed of Usain Bolt. Some people are just built different, and so are chemicals. Some chemicals are just built different. For example, oxygen gas will have many effective orientations, so this makes it more reactive than other things. Fluorine's electronegativity makes it more reactive. Tertiary alcohols, as we discuss them in organic chemistry, will have limited effective collisions due to the fact that their molecular structure is built in such a way that they have limited effective collisions with other molecules. Simple ions like Ca2+ will be more reactive than other complex ions. Now for the final factor that affects rate of reaction, pressure. Here, when we talk about pressure, we talk about compressible stuff. So this will only apply to gases. Increasing pressure of a gas will decrease the volume of that gas, thereby increasing the concentration of the gas in that amount of volume. This will now increase the rate of reaction. We'll see what I mean with visuals. So the more the particles occur per unit volume, so we increase the pressure by pressing on the gas, which means more particles are going to be available per that smaller volume. So you can refer back to ideal gases in grade 11. So you can see how these chapters build up from each other. This one as well is going to build up into chemical equilibrium and so on. So there's no cram, pass and forget, guys. No cram, pass and forget at all. That's a lie that people tell you. Now, when this happens, more particles have enough kinetic energy to overcome activation energy. In other words, more particles have more EK greater than EA. Then we can witness more effective collisions per unit time. This means our rate of reaction increases. So let's look at normal pressure. Our rate graph looks like this. It's going to end at that time. So let's look at what happens when we press on the gas reactants. We're going to now have a smaller volume. So now particles are more compact. They are now colliding into each other with effective collisions. So we expect the rate of reaction to be much quicker. But the volume of the products is going to still be the same. Okay. Now we'll talk about the final topic, which is called the Maxwell-Boltzmann distribution curves. So these curves are going to show us the distribution of kinetic energies of particles. We'll see how as we go on. I'm going to explain these graphs to you, and what you have to know is that the area under the curve to the right of the EA line shows the particles with more kinetic energy. Basically, the area that I'm going to shade to the right of the EA line is going to show you how many particles or the number of particles that have enough kinetic energy for effective collisions. So let's look at temperature. Remember, increasing temperature results in more particles having more kinetic energy to overcome activation energy. So let's draw the number of particles versus kinetic energy graph. On the y-axis, they show us the number of particles. How many particles? Basically the count. Don't be fooled by the area. It's the count of particles. 1, 2, 3 million, thousand, the count of particles. The EA line is the activation energy line. Kinetic energy in kilojoules is on the x-axis. So now we put a small flame on that reaction. For a temperature of that flame, T1, now the distribution looks like that. What does that mean? As you can see, more particles are towards the left of the EA line, which means this area represents the amount of particles that can react. Actually draw a dotted line in green there to show you all those particles. That small fraction of particles in the test tube is going to react. The rest is not going to react. So you can see how very, very unfavorable the reactions are. A small ratio is going to react. Those amounts of particles under the line is going to react, or those amount of particles to the right of the EA line on the Maxwell-Boltzmann distribution curve is going to react. But how can we change that? Obviously, we can raise the temperature up or increase the flame in this case. So when we do that, we can see that more particles now are going to react. The graph is shifting to the other side of the EA line. Now, if you check, all those particles shaded in yellow, including the ones that shaded in green already, are going to react. So all the particles under the yellow line on the test tube are now going to react, or they have more kinetic energy to overcome the activation energy. A bigger temperature line is the dotted red line. This is always tripping students out. So T2 will be greater than T1. If you watch my videos, obviously you know how. Because we want to shift more particles beyond the EA line for them to react. Let's look at the Maxwell-Boltzmann distribution curve for concentration. Remember, increasing concentration increases the number of particles that occur per unit volume. So if we draw the same graph, same EA line, same kind of reaction inside that test tube, a normal reaction looks like this. This is when we have 1 molarity. That big letter M means the units for concentration, which is equivalent to mole per decimeter cubed. This fraction of molecules are going to have enough kinetic energy to react. So now if we now increase the concentration by adding this stuff, now the graph is going to look like this. We have now 2 molarity. So enough particles shaded in yellow are now going to react. Starts by increasing the concentration alone. So all the particles under the yellow line, including the ones under the green line, are now going to react. So you can see how increasing concentration increases the number of particles that have enough kinetic energy to overcome the activation energy. We're going to look at the Maxwell-Boltzmann distribution curves for usage of a catalyst. You know by now that the catalyst lowers or decreases the activation energy so that more particles will now have enough kinetic energy to overcome the activation energy. In other words, more particles are going to be to the right of the EA line. So let's look at the graph again. Here's the normal EA line. Here's the normal distribution. Here's the particles that will have enough kinetic energy to react. You can see the ratio on the test tube. Now, by adding a catalyst, we're literally lowering or decreasing the EA line. So you can see the EA line shift towards the smaller amounts. That's because we add a catalyst. So now you can see more particles have enough kinetic energy to overcome this new EA line. So if you can check on the test tube, more particles will now have more kinetic energy to react. And that's what it's all about. If you have further questions, please address them in the comments section. If you want to join my classes, you can send me a WhatsApp and then we can take it from there. Okay guys, what's important for now is for you to subscribe and also like the video, share it with your friends, make them pass as well, make them use this channel to get that distinction. And then yeah, I'll see you in the next video. Cheers.